Okay, good afternoon. My name is Hongbo Yao from Macau, and today I would like to introduce our recent or initial results about physics-based modeling of Earth's magnetic field. And this is the outline, and my talk will include many three parts: the background, and then I will introduce the field modeling method and the induction equation constraint, and then I will introduce our initial results using MS-1 and Swarm data. So I would like to start from geomagnetic field models. And a geomagnetic field model, it describes the spatial and temporal variations of various magnetic sources, both inside and outside the Earth, including the core, the mantle-induced field, and the crust field, ocean-induced field, ionosphere, and magnetosphere. And currently, there are many geomagnetic field models, and including KELS, SAM, and BGM. And all these models have contributed to geomagnetic field modeling. And for our MS-1 team, we would like to develop a physics-constrained geomagnetic field modeling framework and models which incorporate more physical constraints. For example, in 2024, we incorporate the electromagnetic induction equations in the Earth mantle, so we can better account for the Earth mantle-induced magnetic field. And in 2025, we also incorporate the electromagnetic induction equations in oceans, so we can incorporate the magnetic field induced by ocean circulation. And here in this study, we will focus on core field, and we will incorporate the magnetic induction equation into geomagnetic field modeling. So, and the frozen flux assumption and the magnetic induction equation is the form. And here the dBdt is the circular variation, and the U denotes the core flow, and B denotes the Earth's core magnetic field. And this equation shows that the interaction of core flow and the magnetic field can generate the circular variation. So from this equation, we can involve for the core surface flow if we know the circular variation and the magnetic field data. And in the meantime, it also implies one thing, that the core field models should satisfy the magnetic induction equations. And but in most field modeling frameworks, this physical constraint is not explicitly enforced. So what we would like to do is to extend our previous field modeling framework to incorporate this induction equation constraint. And we also would like to investigate its influence on the core field model. So in our framework, this induction equation is enforced as an additional constraint in the model inversion objective function. And this objective function includes the first term, the data phase between model prediction and the observations. And also, there are two transitional terms which minimize the third and second time derivative of the core field at the comment boundary. And here, in addition to these recognitions, we also apply another recognition which forces the field model to satisfy the magnetic induction equation. And this recognition is the following form. It includes the integration of the magnetic induction equations, also at the comment boundary. And here we can see the core flow and the magnetic field, both are unknown. So this problem is linear. And to solve this linear problem, we apply a iterative approach. And this approach alternatively estimates both the flow model and the field model. And here, this picture shows the workflow of our method. And first we have the data, MS-1 and so on. And then we perform traditional field modeling to estimate the field parameters without the induction equation constraints. Then we use this model to estimate a core flow model. And then we use the core flow model to estimate the field. And then until this process convergence, we have the field and the flow parameters. And it should be noted that this all framework are different from the field flow co-estimation technique. And we use inertial modes to represent the flows in this study instead of the spherical harmonics. And this has two advantages. First, the inertial modes naturally reflect the dynamics of Earth's fluid core. So it can help to reduce the non-uniqueness of core flow inversion. And second, this parameterization can reconstruct not only the core surface flow, but also 3D core flow. And here, this is a subproblem 1, the flow estimation. And here, with a combination of the inertial modes to represent the Earth's core flow, like the form. And these modes are defined in cylindrical coordinates, and it includes 3 parts. The first part is the equatorially symmetric inertial modes, and the anti-symmetric inertial modes, and also the geostrophic inertial mode. And the parameters mk and n count to the spatial complexity of the flow in different directions, and the c coefficients are the unknown flow mode coefficients. And here, the u are the inertial modes, and they are served as pre-computed basis functions. And these basis functions propose the physical structural constraints on the flow. And this picture shows the distribution of about 4,000 inertial modes grid at the comment boundary, and it is computed in physical space. And so using this pre-computed basis function, it can avoid the need for additional regularization during flow inversion. So if we, here is the induction equation. So if we know the magnetic field and the second variation, and we can write this equation in a linear form. And then the flow model parameters can be estimated in least regular least squares inversion. And in addition, and the MS-1 team also developed a more advanced framework using PIN. But here, I will use this simple framework. And here, for the subproblem 2, the field estimation and the induction equation constraints, and we parameterize the time-dependent core field using spherical harmonics up to degree 15. But we also co-estimate the cluster and the magnetospheric fields. But we will not show the results for these 2 fields. And so the inversion objective functions with the estimated flow is known. It is written here. And then the model parameters are estimated using iteratively least square method. Okay, so I will show the initial results using MS-1 and Swarm data. And here, we use over 10 years Swarm constellation data, alpha, bro, and Char-C, and both vector and scalar data were used. And for the MS-1 data, we use over 2 years of vector data. And here, in the following, we will compare 2 models. And the first one, model 0, was modeled without induction equation constraints. So its input is field model. And for model 1, it includes the induction equation constraints. And here, we use, for simplicity, we only use a steady core flow for model 1. Okay, and this picture shows the estimated core surface flows using different truncations of M and K. And here, the first panel shows the core surface flow of a PIN solution, and the right 2 panels shows the structure of the flow model estimated from this framework. And we can see very similar structure. And there we can also see the dominant feature of the flow is a lattice scale west order flow in the low latitude Atlantic hemisphere. And here from the right two panels, we increase the truncation parameter, but we do not see a significant difference. Okay, and here also shows the course flow, but use different truncations of n. And this parameter considers the equatorial symmetry of the flow. And here, the first one, when n equals to 1, and the flow is almost equatorially symmetric, and you can see the symmetric structure. And when it becomes large, and we will see slightly complex structure. So using inertial modes, it can provide a natural structure constraint on the flow. And here, we show the magnetic field model. And here, this picture shows a trade-off curve between the data misfit and the model roughness. And here, show the need of the L cover. So we choose this damping parameter for model 1. And here, we first show the spectrum of the main field in the left and the second variation in the right at approach 2025 for these two models. And model 1 without constraint and model 1 with constraint. And for comparison, also plotted the spectrum of chaos model. And here we can, in the left panel, we can see the three models show similar spectrum, but in the right panel, we show that after imposing the induction equation constraint, we can see a very clear difference in the SV spectrum for model 1. And this is because this field model is forced to satisfy the induction equation. So I think this is a result of a trade-off between data fate and physical constraints. And here, I show the global map of the circular variation at Earth surface in the left, and also the difference between model 0 and model 2 in the right panel. And here our model was resolve the typical structure of the circular variation at the Earth surface. It is strong SV single in the north, eastern South America, and also the negative and positive SV field in the west and the east of South Africa. And in the right panel, we see that after enforcing the induction equation, and we see distinct difference. And this is caused by the enforcement of the induction equation constraints. Okay, and here, I show the same maps, but at the commental boundary. And at the commental boundary, there are more small-scale structures in the SV map. And here, but the second variation difference becomes more remarkable at the commental boundary, and it can reach up to 10 meter per year. Okay, and here is summary. And this is only our initial results. So in this work, we extended our framework to incorporate the induction equation constraints. And using this framework and MS-1 and Swarm data, I obtained self-consistent models of the core magnetic field and the flow. And the flow model satisfies the induction equation, and the core flow model is constrained by the inertial modes. And what we would like to do is to explore a better choice of the truncations of the inertial modes, which counters the spatial complexity. And we will also consider a time-dependent core flow. And okay, thank you.